Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at the nucleophilic substitution reaction between a halogenoalkane and hydroxide ions, forming an alcohol. We're going to talk about why and how this reaction happens, outline the reaction mechanism, and look at how carbon-halogen bond strengths can be compared by looking at the rates of hydrolysis for different halogenoalkanes using aqueous silver nitrate. Other reactions and mechanisms of halogenoalkanes have been covered in separate videos. Check the links in the description below. Before we talk in detail about the reaction, there are a few essential ideas you need to be comfortable with. Halogenoalkanes, also called haloalkanes, are a group of compounds that contain an alkyl group, carbon and hydrogen chain, bonded to a halogen, fluorine, chlorine, bromine or iodine. In simple terms, they are like an alkane where a halogen has taken the place of a hydrogen. Alcohols are a group of compounds that contain an alkyl group bonded to a hydroxy group, OH. Apart from with iodine, the carbon-halogen bond in a halogenoalkane is polar due to the halogen's high electronegativity and carbon's low electronegativity. This means the halogen pulls the electrons in the bond towards itself slightly and as a result has a partial negative charge, and the carbon it is bonded to has a partial positive charge. As halogen size increases down group 7 in the periodic table, from fluorine to iodine, the covalent bonds they make to carbon get longer and therefore weaker. This means a carbon-fluorine bond is very strong and has a very low reactivity. A carbon-iodine bond, however, is weaker and more easily broken, making iodoalkanes much more reactive. The nucleophile is an electron-paired donor that is attracted to a positively charged or electron-deficient atom. Nucleophiles can be negatively charged and always have a lone pair of electrons. A substitution reaction is where one group or atom in a molecule is swapped for another group. In organic chemistry, we show the possible steps occurring in a reaction by using mechanisms. Curly arrows are used to show how a pair of electrons move as bonds get broken and formed. The arrowheads always point towards where the electron pair is moving to. Recap done? Let's go. Halogenoalkanes can react with hydroxide ions in aqueous conditions to form an alcohol. A hydroxide ion is able to act as a nucleophile as the oxygen in the ion has a lone pair of electrons that can form a bond to an electron-deficient atom. The carbon atom bonded to a halogen in a halogenoalkane has a partial positive charge, and this makes it vulnerable to attack by nucleophiles, nucleophilic attack. When a halogenoalkane is mixed with aqueous hydroxide ions, the hydroxide ions get attracted to this partially positive carbon and a bond is formed between the oxygen in the hydroxide ion and the carbon. At the same time, the carbon-halogen bond will break with the bonding electron pair going to the halogen, forming a halide ion. The original halogenoalkane has become an alcohol. The species starting the reaction, the hydroxide ion, acts as a nucleophile, making the reaction nucleophilic, and a hydroxy, OH group, has been substituted for the halogen in the molecule, making the reaction a substitution reaction. This is why the reaction and mechanism is described as nucleophilic substitution. There are actually two different ways this reaction can occur depending on the type of halogenoalkane reacting, and they are referred to as SN1 and SN2 reaction pathways. The examples shown in this video are SN2 as primary halogenoalkanes are used. For tertiary and some secondary halogenoalkanes, an SN1 mechanism occurs where the carbon-halogen bond has to break before the nucleophile, OH-, can form a bond to the carbon. SN1 and SN2 reactions have been covered fully in a separate video. Check the links in the description below. As an extra note, if the reaction is carried out in ethanol, ethanolic conditions, rather than in water, aqueous conditions, an elimination reaction can occur and an alkene is formed instead. Again, this has been covered in a separate video. Check the links in the description below. Let's have a quick recap of this reaction and mechanism using bromoethane and sodium hydroxide as an example. A hydroxide ion is attracted to the partially positive carbon from the carbon-bromine bond, and a new bond is formed between the oxygen in the hydroxide ion, with a lone pair of electrons, and this carbon. At the same time, the carbon-bromine bond breaks and the bonding pair of electrons goes to the bromine, forming a negatively charged bromide ion. An alcohol, ethanol, is produced. In these substitution reactions, the carbon-halogen bond must break before the alcohol can be made. The easier it is to break the carbon-halogen bond, the faster the alcohol can be formed. Due to the size of the halogen atoms increasing, carbon-halogen bond length increases as you go down group 7 in the periodic table, and this makes the bonds weaker, meaning carbon-fluorine bonds are the strongest and carbon-iodine bonds are the weakest. As a result, iodoalkanes will react more quickly than bromoalkanes, and bromoalkanes will react faster than chloroalkanes. Carbon-fluorine bonds are so strong that fluoroalkanes won't react at all to form alcohols. As the carbon-halogen bond breaks, a halide ion is released. We can use this releasing of a halide ion to detect when the reaction has finished. If the reaction is carried out with aqueous silver nitrate in the mixture, as soon as halide ions get released during the mechanism, a silver halide ion precipitate is produced. By timing how long it takes to form a precipitate, the relative rates of the reactions for different halogenoalkanes can be compared. Chloride ions form a white precipitate of silver chloride, AgCl. Bromide ions form a cream precipitate of silver bromide, AgBr, and iodide ions form a yellow precipitate of silver iodide, AgI. Silver nitrate is used as it's a great source of silver ions, as silver nitrate is readily soluble in water, and the dissolved silver and nitrate ions don't have any impact on the actual substitution reaction occurring. The silver ions just simply form a precipitate with the halide ions as soon as the halide ions get released during the alcohol formation. So, to summarize, halogenoalkanes can react with aqueous hydroxide ions in substitution reactions to form alcohols. The reaction is an example of nucleophilic substitution. Hydroxide ions have a lone pair of electrons and can act as a nucleophile, bonding to the partially positive carbon atom from a carbon-halogen bond. As a hydroxide ion forms this bond, the carbon-halogen bond breaks with the bonding electrons going to the halogen, forming a halide ion. This is more specifically referred to as an SN2 mechanism and occurs when primary and some secondary halogenoalkanes react. For tertiary and some secondary halogenoalkanes, a different mechanism occurs called an SN1 mechanism, where the carbon-halogen bond must break before the oxygen can make a new bond to the carbon. The rate of reaction is determined by the strength of carbon-halogen bond in the halogenoalkane. As halogen atoms get larger as you go down group 7 in the periodic table, the carbon-halogen bond gets longer. This makes the carbon-halogen bond weaker, and as a result, it can react faster. Carbon-fluorine bonds are too strong to break in these nucleophilic substitution reactions, making fluoroalkanes unreactive. Iodine carbon bonds are weaker than bromine carbon bonds, and bromine carbon bonds are weaker than chlorine carbon bonds. As a result, iodoalkanes react fastest and chloroalkanes slowest. Halide ions released during the reaction can form precipitates with silver ions. By timing how long it takes to form a precipitate, the relative rates of such reactions can be compared for different halogenoalkanes. Chloride ions form a white precipitate, silver chloride. Bromide ions form a cream precipitate, silver bromide, and iodide ions form a yellow precipitate, silver iodide. Silver ions are added to the reaction mixture in the form of silver nitrate. The silver and nitrate ions don't interfere with the substitution reaction. If the reaction between a halogenoalkane and hydroxide ions is carried out in ethanol rather than water, the hydroxide ion acts as a base rather than as a nucleophile. An elimination reaction occurs and an alkene is produced. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.